we change hats. So I want to thank the organizers for inviting me. And now we will be talking about machine learning.
Iordanis.
Yes?
Lightning talk. What is it? Is it
It's a 5-minute...
So is it open problems or is it...
It's anything you like. It's, we have 1 hour free for people who are not giving talks to actually speak about something that they think is important. It could be an open question, it could be a comment on something else, it could be a new paper, it could be something, right? The idea is we want to start discussing about things. So think of it as an opportunity to start a discussion with other people who are here, more than announcing a result. Okay, good. So the first session today is about machine learning. So as Umesh said, we will have a couple of talks, and then at the end there will be a discussion. And I start with quantum machine learning prospects and challenges. So there are many prospects and many challenges. So let's see. So why should we look at quantum machine learning? Well, you kind of already know how hyped machine learning is, and you can find all these fancy pictures on the web about machine learning. Then if you put quantum, then it becomes even more hyped. But I really think that, as Umesh said, that we really need to solve a main problem, and this is we need to find some real-world applications of quantum computing, right? So we don't have that many ideas. That's why algorithmic research is important. And I think machine learning is one of the areas where we should keep working on. Okay, I'm not saying that this is the area where we will find the killer app, but I certainly think it's the area that we should still looking for applications. Okay. So here are some reasons why. Well, there were reasons for optimism. It's mostly reasons to keep working on these things. So we do have some powerful quantum tools, right? And we have powerful quantum tools that are very useful for classical machine learning. And these have to do with linear algebra. So if you go and you look a little bit more carefully in machine learning, there's a lot of linear algebra happening here. And linear algebra is one of the things that we kind of know that quantum computers could help, right? So kind of it's a match there. So let's try to see how can we use these quantum tools for linear algebra to say something interesting about machine learning. The second is that we also have something called, we can estimate distances between quantum states. If I give you 2 quantum states and I tell you how close or far are they, then you can all come up and say, I can do a swap test, and I can estimate fast, something about the inner product or the distance of the states. So this is also something which is useful in machine learning. There's another reason why I think it's an interesting field is that machine learning already has to deal with a lot of noise because the data is very noisy. Many times, even when we train neural networks, we add artificial noise while we're training the neural networks because we want these things to be very robust against noise, right? So I'm not saying that this is something that necessarily will help, but it's not a bad thing that, we need to come up with algorithms that have to deal with noise. Quantum computers will be noisy. We might, get away with the fact that they're noisy computations because we do want the computations to be noisy when we're doing machine learning in some sense. Right? Okay, there's also another thing is that there are many different things that you may want to actually do in machine learning. So one of them is let's do things faster, and this is great. But there could be other things that are equally important, which is, for example, things like explainability, like energy consumptions, like trustworthiness. So these are things that people have started talking about a lot in machine learning. And there are algorithms that are more explainable than other ones. Maybe they don't give you the best accuracy, but even that, if you can, do something quantumly better in that type of algorithm, maybe you don't get the best speed or the best accuracy, but you will get other properties like explainability, right? And this becomes more important the moment you start talking to people, like people in healthcare, that they want to use machine learning. They cannot use machine learning if they cannot explain why they're taking a decision somehow, right? Okay, so there are even more reasons why we should keep working on it, and this has to do with the fact that it's not obvious how to get real-world applications in machine learning because there are also many subtleties in these things. So the first thing is that all these quantum tools that I said about linear algebra, they are very subtle in the sense that it's not a clear-cut algorithm that says that, okay, you give me the problem, I know how it's going to run, worst-case analysis, this is what will happen, and you know when you're going to get the speed up or when you're not going to get the speed up. So you really have to look a little bit under the rug and really figure out what matrices are you dealing with, what kind of properties your data have, and all these type of things can make your algorithm work fast or not fast at all. So somehow you need to get more into the details of the use case and of what you're trying to solve if you want to understand whether quantum algorithms will give you some advantage or not. Okay. There are also issues about how do we load classical data as quantum states. There are also issues about the fact that all these linear algebra tools will give you a quantum solution at the end. But at some point, you might actually want a classical solution because you want to solve a classical problem. So how do you deal with this type of things? And I'll talk more about these things. And the last thing, which is a very big drawback, is that we need to benchmark machine learning. And the only way really to benchmark machine learning is whether it works in practice or it doesn't work in practice. And it's very difficult to try to benchmark quantum machine learning when we don't have the machines to actually run and see how things actually run. So there are different ways of dealing with this, but it would be great to have better machines so we can actually start testing all these things, apart from studying them or simulating them. And this will come with, as soon or as not so soon as hardware becomes better. Okay, so I split my talk into three different segments. One is about supervised learning, the other is about unsupervised, and the third one is about reinforcement learning. These are the three main topics in machine learning. I will spend most of my time on supervised learning, but I will try to say a few things about the other two towards the end of the talk. Okay, so let's start with classification. I just copied here a list of applications of classification from Wikipedia, so I don't understand half of them, but just to show that there are many applications of classification, okay? And I wrote here three different types of ways that people are trying to do actually classification. Okay, so what is classification? You have a bunch of data points. Some of them are labeled, some of them are not labeled. You want to learn from the labeled data that you have so that when a new data point comes, you can put a label. For example, you want a machine that if you train the machine on how to recognize hundreds and digits or cats and dogs, then at the end, if a new photo comes, then the machine should say this is a cat or this is a dog or this is a 3 or this is a 1. Okay, so this is on image recognition. Then you can have also things about text, natural language processing. But the main ways of trying to solve this problem, one of them is what I said, has to do with distances. So what do you do when you want to figure out if your image or if your data point is, belongs to label 1 or label 2? You kind of try to figure out if you're close to other points that are labeled 1 or you're closer to points that are labeled 2, right? So you take all these data points, you embed them into some space, some Euclidean space, and then you try to understand through your neighborhood, how close are you to specific data points, and this is how you try to assign a label to yourself somehow, okay? So these are things like k-nearest neighbors or nearest centroids and things like that. The second thing that is used more in practice nowadays on how to do classification has to do with neural networks. So you take your favorite neural network, it could be a convolution neural network or a fully connected neural network. You train this neural network on data that are already labeled, and the hope is that at the end, your neural network has been trained enough so that if a new point comes, then it will tell you the right label at the end, okay? Other things, there's this thing called support vector machines. You will hear a talk about this afternoon and more stuff. So let's look a little bit on the first one that says about distance estimations, right? So this is kind of one photo. This is how, let's say, nearest centroid works. You have the blue points, the green points, and the red points, and then a new point, this white one, comes into the picture, and you have to say, is it going to be blue, green, or red? So what you do is that you look at the centroids of these clusters, and then you say, okay, let's find the nearest centroid, and then assign the corresponding label. Okay, it's kind of a normal, algorithm of this type. So as I said, there is one thing that we could try to do quantumly fast, which is exactly try to figure out what is the distance between two quantum states, okay? So let's assume for now that you know how to construct these data points U and V, okay, as quantum states, and I'll discuss what this means. If you know how to construct, let's say, U and V, you have a circuit, you can construct easily this state here, which is like 0 U plus 1 V, so you kind of construct the state. And then if you just Hadamard the first qubit, then you see that the probability that you get 1 is exactly proportional to the Euclidean distance of the points in some sense. Okay. So, of course, there is one more thing that you can do apart from just counting how many zeros and ones you can do. You can also do something like amplitude estimation, and you can estimate the probability of 1, for example, and then in time, which in principle can be quadratically better than classically, you can estimate the distance between these 2 points, u and v. Okay? So this is a very tiny quantum thing that one could try to do. I'm not saying that this will save you and will give you the killer applications, but I'm just saying that there is a way of getting some modest improvement, which is a quadratic improvement on estimating distances between quantum states. Okay, then the second thing I talked about is neural networks. So this is a big field of research. So I just copied a few of the proposals of quantum neural network architectures and what they look like. I don't understand all of them, but the main idea is the following. The main idea is that you start, let's say, with an image. You embed the image into a number of qubits, and then you have some sort of quantum circuit which has gates that have some parameters. Okay? And let's say, the first qubit here, if it is 0, then you should say cat, and if it's 1, it's supposed to be a dog. So you start with something that is some sort of random circuit that doesn't give you the correct answer many times. And then what you do is that little by little, using the data that you already know the labels, you try to figure out what these parameters should be so that at the end, you are mostly correct on this label of cat and dogs. And if you're mostly correct on the data that you already know, you hope that when the new image comes, then this neural network will actually, also give you the right label of the image. Okay? So this is kind of the idea. So classically, this is exactly the same. There are parameters which have to do with the weights that you use in order to go from one neuron to a neuron of the next level. Here, the idea is that you just start with some unitaries and some parameters, and you try to figure out what these parameters should be. Okay? I think Xiaodi, after my talk, will talk more about how to use these type of things to do some interesting stuff.
Okay. Question?
Yeah.
Gradient. So do you again apply gradient distance, stochastic gradient distance here? Or
So it's an interesting question. So to be fairly honest, there are many of these proposals that don't even talk about training. So there are proposals that talk about training, and the training is some sort of gradient descent computation, some stochastic gradient descent, yes. Okay, so it's an interesting research area. We have some small examples that these things could actually work. Okay, it's very difficult to benchmark these things because we don't have these quantum circuits to actually run in sizes that will actually make sense to understand whether they will scale well and whether they will work well. Okay. There's one comment that I also want to make is that this type of techniques can be very useful for specific type of problems, like start with a circuit with some parameters and try to figure out what these parameters are. But certainly not all problems are amenable to this type of techniques. There was a blog post by Scott recently that kind of says the obvious, that you should not expect to solve factoring, for example, with this type of techniques. But whether you can actually do something interesting with classification, why not? I mean, classical neural networks work, so it's possible that we figure out nicely how to work with these things. Okay, so we also did some work on neural networks, but here we tried more to look at classical neural networks. So we don't want to define a new model. We looked at the classical neural networks, and the question was, can I do the training faster through a quantum algorithm? Right, and as we said, the algorithm for training has to do with gradient descent, so there's a lot of matrix multiplications and linear algebra, and this is where we want to use quantum linear algebra to do something interesting here. You can start getting gains just from the fact that you can use some sort of estimation of the inner product of these things. This is not going to give you too much of a gain. Like I think the best you can hope compared to classical ways would be a quadratic speed up on one of the terms, but this could be interesting. And then we also looked at convolution neural networks where there is a little bit more work to be done because there are all these different kind of operations that one does on a convolutional neural network. This was a paper from ICLR. Okay, so the main channel for this to me is how to combine two things, right? We do want to look at quantum neural networks that we can actually implement, like in the NISQ era, and these are not like that, so we have to go back to the previous one. At the same time, it would be good to have some provable guarantees. So now what do I mean by provable guarantees for a neural network? It's, even for classical neural networks, sometimes we don't know why they actually work. But there are statements that you can try to prove here. For example, you can say that at least it can do as well as the equivalent classical neural network, for example. Could do better. Maybe I don't know how to prove that it can do better, but can we at least prove something of the form, if the classical equivalent neural network would work, then this could at least do as well as that. So this type of, trying to find some sort of evidence why we would believe that these quantum neural networks would actually work or not. Okay, so there is one other thing that I want to discuss a bit on classification, and this is very interesting when we will start talking about the input, is the fact that many times when I give you the data as an image, let's look at the MNIST data set is like 780 something pixels. The first one thing you can try to do is just use exactly that as your input, right? You just write down the vector that corresponds to the pixel. This gives you some sort of data point, and you start trying to classify with these points, right? But many times what people actually do is before doing that, they map all these data points into a space where the classification is much easier or much more accurate to do, right? So these are all these type of techniques that are called, for example, dimensionality reduction. So you would think that dimensionality reduction reduces the dimension, which is true, and why would it be better than keeping all the dimensions? But many times what you do is actually you start from your input, you go to a bigger dimension, and then you bring it down to a smaller dimension, and somehow this gives you keeps the information that you need and gets rid of the information that you don't need, right? So these are things like principal component analysis, linear discriminants, low feature analysis. So all these type of things try to find the best way of embedding your data into a new space and then using some normal classification algorithm within that space. Okay? And why is this interesting? Because here in the classical, the reason why these are, are difficult to use in practice is because this is some much heavier linear algebra now, right? So all these kind of techniques have to do with basically looking at the eigenspaces of these matrices. Like you need to find the eigenvectors you can project on the top eigenspace, or for example, you look at the low eigenspace of the covariance matrix of your data. So there is some more heavy linear algebra that has to happen here. And this is, again, one place where quantum can actually do something better because we can hope that quantum can do this type of linear algebra operations faster. Okay. So there have been results on quantum ways of doing this type of dimensionality reductions. Okay, so we use some sort of quantum linear algebra to do this mapping from one space to the other. And then, as I said, you can use whether you want a neural network or you can use a nearest centroid type classification algorithms to work in this new space. Okay. So here is a way of actually doing this type of things in a quantum way that can actually provide some advantage to you. So I think probably everyone has heard the phase estimation algorithm. I give you a unitary, I give you an eigenvector of the unitary. Then what a quantum computer can do fast is basically estimate the eigenvalue that corresponds to this eigenvector. Okay? So now the singular value estimation is basically an extension of the phase estimation that says that, okay, if you give me a matrix which may not be a unitary, but let's say it's a symmetric matrix for now, it has some decomposition on eigenvectors and eigenvalues, and then there exists a quantum algorithm, there exists a circuit that if the input is an eigenvector of this matrix, then it will estimate the corresponding eigenvalue. Okay, it's not going to give you exactly the eigenvalue. They're going to be like an epsilon approximation of this eigenvalue. And the good thing is that you can do this in superposition, right? It's a quantum operation. So how does this relate to doing these things? So here is a very simple example. So imagine that what I want to do is that I want to project a vector onto the eigenspace of this matrix that has high eigenvalues. Okay? So let's say I have a threshold T, and I want to project B on the sub-eigenspace of A with eigenvalues that are more than this threshold T. Okay? So here is a simple way of understanding how we can do it. It's not necessarily the best way when it comes to the errors, but it's easy to explain. You start with your vector, okay, and you can imagine that this vector has some decomposition in the eigenspace of the matrix. You don't have to know it, okay, but it can be written, in this way. And then if you feed this vector here, which is just your initial vector, into this procedure, then what will happen is that next to each one of the eigenvectors, you'll come up with an estimate of the eigenvalue, of the singular value, let's say, okay? And then once you have this value here, which is like a number that you write with some digits, then you can do a simple operation that says that, okay, look at lambda. If lambda is more than t, put a 0. If lambda is less than t, then put a 1. So some sort of threshold gate, which is a simple thing to do. Look at this register, keep the ones that are bigger than the threshold, get rid of the ones that are smaller than the threshold, okay? And then if you measure 0, or if you post-select here on 0, then the state here, and then you uncompute the lambda, the state here is exactly what you would want for something like this, which is the projection of the vector onto some part of the eigenspace of this matrix. Okay? Here we did the top eigenspace. It could be also the lower eigenspace. You can decide things that have to do with the eigenvalues of this matrix. Okay? So this is another case where you have this quantum algorithms for linear algebra that can help you in doing some more complicated classification algorithms. Okay? Okay. So what is the runtime of these things? Yeah.
Measure the 1, you're lost.
Yes. So either you do, basically what you can do is you do amplitude amplification so that you end up with this state. Or if you know how to construct the state, you just measure until you get 0 if you want a slower but faster algorithm. Yeah. Okay, so what are the parameters that come into this linear algebra things? We usually talk about 3 parameters. This kappa has to do with the condition number of the matrices, like what is the lowest eigenvalue of the matrix. Nu is something that could be the sparsity of the matrix, or could be the Frobenius norm of the matrix, or it could be something like the max L1 norm of the rows of the matrix. So there are different ways of constructing these matrices that you are going to get different parameters here, okay? But this is something that depends on your data, on your matrix. Is it sparse? Is it is it sparse? Does it have a low rank or high rank? What is the Frobenius norm? Different. You can decide which way to embed your matrix so that you can get different parameters mu here. Okay. And then there is a parameter epsilon, which depends on how well you are doing the singular value estimation. There are algorithms that actually produce quantum states with log 1 over epsilon. Okay, but if you want to actually look at this, then the samples that you will need is again 1 over epsilon square. So somehow there is a 1 over epsilon, or log 1 over epsilon, depending on what you claim you have at the end of the quantum procedures.
This kappa is the conditional number of the matrix, or the distinctions that you want to make?
So there are different things. For example, here, the kappa is very simple. The kappa is like t over 10, right? So as long as your t is something reasonable, for example, it could be 1 over the rank if you want the top k rank things, then your kappa is basically this threshold. The most difficult thing would be when you really want to do the inversion of the matrix to solve the linear system, and then you have to care about the smallest eigenvalues, let's say, right? When you do matrix multiplication, you don't care about this kappa. This kappa shouldn't appear in the running time of a matrix multiplication algorithm, for example, right? So again, depends on linear algebra is not the same. Matrix multiplication in linear systems is not exactly the same thing, even though it's the same n to the mega. It's not the same thing somehow, right? Okay, I wanted to talk about 10 minutes. I have about recommendation systems very briefly. It's 1 slide and a half. So this is kind of the first example that we came up with a few years ago on, well, here is an application of quantum machine learning. Obviously, you will need a very big and nice quantum computer, but at least if you would have your favorite quantum computer, then you could be able to do something. And why do we think that you can do something? Because recommendation systems, it's basically linear algebra. It's basically completing a matrix for which you have a little bit of information, knowing that the matrix has a good low-rank approximation. If you look at the algorithms, then it ends up that you have to do the singular value estimation, because the main point in recommendation systems is, again, you need to do some sort of singular value decomposition. You need to project your rows into the top eigenspace of this completed matrix somehow. Okay? So I kind of showed you how you can do this type of projections through the singular value estimation. And this gave you some sort of competitive recommendations. You know, a few years ago, I would say exponentially faster. So now I say fast. And the reason is that, you know, here is a little bit what the running time of these things are. So here is the quantum thing. The quantum thing depends on the types. Let's say the types of the users is basically the rank of the matrix or the Frobenius norm of the matrix. So this is something fairly small compared to the dimension, okay? But it only depends logarithmically on the dimension of the matrix, right? And this we were kind of contrasting to the work that we did a long time ago with on recommendation systems that, you know, it's also a coincidence. I was an intern with one of Ravi's students, Petros, and with Prabhakar Raghavan. It was exactly the time when they were coming up with these amazing kind of techniques for randomized linear algebra. And when we were looking at it, we said, okay, the recommendation system is the right application to apply it. So we came up with how to do recommendation system based on the CUR techniques for randomized linear algebra. I think Ravi will talk more about this. And the running time there was, you know, again, type squared times the products. So this is why we were claiming the exponential speedup, because you don't have to depend on the products anymore. You can go to the log of the products, okay? So this was kind of the story until 2017. And then there was some really good work by Erwin Tank, who also will give a talk after the break, who said that, okay, so this is what you get if you look at the CUR-based techniques, but there were some techniques which were there even before, which is the FKV techniques, that actually do not have to depend on the dimension. They can also depend on the log of the dimension. You do have to pay a penalty, and it's kind of a steep penalty that, you know, I think we shouldn't neglect, that the polynomial on the number of types that you have here is something like 20 to the power of 24. I looked at this paper, which I think it's improving on this paper, which if you just put some sort of numbers that happen for the Amazon matrix, you get something which is the number of the atoms of the universe. But this doesn't mean that this algorithm runs this. This is what somehow the theoretical bound gives you, and I will discuss a little bit more what these numbers mean, okay? So as you see now here, we only have a polynomial gap, because this is log, and this is log, and this is types, and this is polytypes. But somehow you might even get a bigger gap than you had before, because, you know, polynomials can be bad sometimes. Okay, so in the last 5 minutes, I will try to discuss a little bit a couple of things that, you know, maybe it would be good to understand, because this will tell us how to try to keep working on finding real-world applications. The first one is about loading data on quantum states. Okay, so this is one of the problems that people say that, okay, but if you want to run your quantum algorithms, you assume that you have this quantum access, meaning that you have quantum access to this classical data. How are you going to build this type of things? So the first thing, the answer is that you try. So you try, because first answer could be that even quantum inputs can actually be very interesting sometimes, and I think Xiaodi will talk about this. You do have applications where your input is by itself quantum. It's not classical data that you have to take into quantum inputs. You have quantum data that come from circuits that you want to train, for example, or you want to understand the behavior. So there are things that quantum machine learning can do for quantum inputs, so then you obviously don't have the problem of taking classical data into quantum data. There are also many cases where the input is actually easy to construct. So what do I mean by that? So these are the cases where the input is not cats and dogs, but these are inputs that you can actually have a function that actually computes inputs for you. So this is, for example, the case when you try to do PDEs, like partial differential equations through neural networks. There your data is actually looking at your PDE and computing the value of the PDE on some specific points, on some points on your grid. So this is your data, which is easy to construct in the sense that you just apply your PDE and you find the values, right? So there's no extra classical data that you would have to somehow figure out a way of accessing quantumly. There is a circuit, there is a classical circuit that computes data for you.
And your end goal is to do what?
To train your neural network, that then it will give you the correct answer for all your space. Like somehow that the function that the neural network would compute at the end is the solution to your PD, right? It's also the case for reinforcement learning, for example, where your data has to do with your transition matrix. And many times the transition matrix, you know what it is. You have a robot in a room, you know that the robot can go back, front, left, and right. So again, there is no external data that you have to remember or put into a QRAM. You can construct your data as you go. Okay. If these are not the cases, then you also have ways of loading classical data on quantum states. These are circuits that have order D size, meaning that if you want to upload a D-dimensional vector, then you have to pay D on some resource, okay? But you could do it in a way that the depth of the circuit is only log D, so you could say that the circuits could actually be running in log D time in some cases. Okay. As I said, another case is when your quantum input is not really your input, but it's the input after you did some heavy linear algebra on it, like you projected onto the principal components or something like that. So there, the bottleneck is not really uploading the classical data into the quantum data, is how you do the linear algebra. So you can even afford to pay linear on the dimension or linear on the data set, because classically you already pay like cubic on the data set if you want to do this type of pre-processing, okay? So this is another way that you could be getting a polynomial speed up without having to assume anything that you can do on how to upload the quantum data. And sometimes it will not work. So I think the point is that we should really try to understand when it works, when it doesn't work, and for what applications it makes sense. So on the output, again, the question is, you have these quantum linear algebra techniques, you have these quantum algorithms, you come up with a quantum solution at the end. How do you get from this quantum solution to a classical solution of the classical problem that you're trying to solve, okay? So sometimes the quantum states are good enough, and they're good enough because you just need to sample from the solution. You don't need to write down the classical solution. So this is the case for recommendation systems or for classification, for example. Sometimes it's not enough. And when is it not enough? Usually when you want to do iterative methods, meaning that you have some linear system that you want to solve, and then the solution of this linear system kind of defines the next linear system that you would want to solve. So there you have to define your next linear system, so you need the classical information of this quantum state, right? So there, what do? You have to pay more. So you have to pay more, you have to figure out ways of coming with, getting the classical information out of the quantum states. Again, you have to pay a lot. You have to pay proportional to the dimension if you want L2 guarantees, okay? It is, in many cases, it is the case that L infinity guarantees are good enough for you. So this is the case, for example, in reinforcement learning. So all the convergence happens in L infinity. This is also the case with all these new linear programming classical algorithms where L infinity guarantees are good enough. And L infinity guarantees are much easier to get than L2 guarantees, right? So you need the 1 over epsilon square samples from the state, which are independent of the dimension of the state, to get an epsilon close in L infinity classical description of this quantum state, okay? So this is another open question which is quite interesting to me. What is the best classical linear system solution that gives you L infinity guarantees? Not L2 guarantees. For L2 guarantees, we kind of know what's happening. many cases we need the infinity guarantees. We know how to do it quantumly in a nice and fast way. What would be the best classical way for doing this? It's not clear. So, okay, again, in some cases, it's not going to work. And maybe I finish with this slide. So how do we benchmark? How do we know if it's going to work or if it's not going to work? It's not a clear. I think that there's no clear answer to this, and especially I want to make sure that we all understand that there's no one-bit answer that will resolve this issue. So I think the question of is it an exponential or a polynomial speedup, I think it's a very important question because it kind of forces us to look at the right theoretical models between the quantum and the classical thing and really, compare the right things with the right things, okay? But if the answer is that we're going to get polynomial speedup, which is actually the case, this does, to me, it's not the end of the story, okay? So as we said, many times the polynomial gaps could be bigger even than the exponential gaps for what you care about, okay? But what it really matters is the practical scaling, right? So for example, if we look at this algorithm here, okay, there's no way that anything to the 24 is actually going to work. But the question is this really the thing, or is it just a matter of making this better, or can we get better things? So I don't know. So this is very good questions. Like how much can we push these FKV type techniques to get more practical running times, right? So some people did some experiments and they showed actually that the good news and bad news in the sense that this type of algorithms have significantly smaller run times than their worst case complexity, so they don't run as k to the 20 something, okay? But still, they're worse than the previous classical algorithms, so they're unlikely to alter the set of problems where quantum algorithms may have a practical impact. In the sense that you obviously you have to compare with both, okay? So we need to figure out, which one of these is better, or actually use both of them. But somehow it's still open whether this quantum running time can be done in a way, can be seen in practice. Yeah.
Specifically for linear algebra algorithms, or
so this one is. I mean, I put it like this is the recommendation system. It depends. So it depends on what you use from linear algebra. If you do simple things like inner product estimation, then you get kind of a quadratic slowdown. If you do things like projections, SVDs, and things like that, then you get bigger things. If you do even more complicated things like interior point, like trying to support vector machines, then I think I'm not wrong, but the exponent that the paper has is 88. So linear algebra is not the same. It depends on what you want to do. And what I'm trying to say is that the quantum things can do heavy linear algebra stuff, and maybe this is where we can expect to get some speed up, because this is really where the classical methods fail. Okay. So it's a more nuanced question, and I'm done here. Thank you.
Maybe time for a question while the next speaker sets up.